Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is another video in a series on plane curves and parametric equations. You should already have covered the videos or watched the videos on the concept and definition of plane curves and parametric equations and how to graph by eliminating the parameter. In this video, we're going to talk about using technology, which I've already shown in some of the previous videos, but it's probably a good idea for me to actually talk you through how to use Desmos and technology to graph curves. So we're going to go ahead and take a look at this one right here. X equals a, where a is just going to be a parameter that we will change just to look at different versions of this curve. So x equals a plus cosine of t, and y equals a tangent of t plus sine of t. And by the way, this family of curves is known as the conchoids of Nicomedes. All right, let's go ahead and do this. So here we are in Desmos, and the way you can graph a parametric curve is just by starting a point with a parenthesis, just like you would like 3, 4 or something like that. And then type in whatever your parametric equations are. For example, if x were the cosine of t and y were the sine of t, you'd put cosine of t, comma, sine of t. Of course, that's not what we're graphing here. We're graphing a, so I'll put an a in front of that, times the a plus the cosine of t. And the second function was a tangent of t plus the sine of t. Notice that it doesn't graph anything because it doesn't know what a is. So I'm going to add a slider by clicking that button, add a slider. And this just allows me to change the value of a here, which doesn't look like very much. And the reason why it doesn't look like very much is because our time values that it's graphing here only go from time 0 to time 1. And cosines and sines, at least, have domains that are much larger than that. So let's go from time -4 pi to +4 pi, just to see what that looks like. And I will zoom in slightly so we get a better view. And now when you adjust a, you get some very beautiful curves. Look at this right in here. It's very, very neat. So these are the conchoids of Nicomedes. And these are just really beautiful curves. Again, I only did from 0 to, or from -4 pi to 4 pi. It doesn't actually get much more than this. So it's not like you're going to see much more, but this is how you would graph a parametric curve that also has, by the way, parameters other than t. It's very, very neat. And it gives you a wonderful view of the fact that technically, in terms of x's and y's, these are not functions of x's and y's normally. So this is definitely not a function of x because it doesn't pass the vertical line test, but it's also not a function of y because it doesn't pass the horizontal line test. However, turns out that x is a function of t and y is a function of t. So separately, the components are definitely functions. You can play with that all day long. This next example is a set of curves known as epicycloids. And you can see it's very, very weird looking, right? You have a quantity a plus b times a cosine of t minus b times a cosine of quantity a over b plus 1 times t for x, and so on and so forth. This is something you definitely would not want to graph by hand, but let's go ahead and showcase again how we graph these by hand. And I'll add in a little extra here this time to showcase how you could determine the path of travel for the particle. So again, I just started Desmos. I start a point here and I type in, it was the quantity a plus b, let's hop outside of that quantity, times the cosine of t, minus b times the cosine of the quantity, yeah, I know a lot of parentheses, right? A over b, hop outside that or outside that fraction, plus 1, and then t. That ends that first full statement. Now I'm going to go to the y value. The y value was the quantity a plus b end quantity times the sine of t. It's very complex. Minus b times the sine of the quantity a over b. Hop outside that fraction, add 1, hop outside that quantity, put a t there, and that should be the end of it. Now you notice we don't have anything graphing here. It's because we don't have parameters set for a and b, so I'll just click set all. Again, same issue as last time. Notice that this only has a part of our curve. So let's go ahead and go again from a negative 4 pi to a positive 4 pi. Now, some people will say, how do I know, or they'll ask, how do I know how far to go? The reality is probably in this case, you don't need to even go to 4 pi, but I don't really know. I don't know how far to go. I'm just kind of getting some guesses, but you can see what happens as I increase a, you get these beautiful graphs. And if you think that you might get more from it by putting to 8 pi or to 20 pi or to 200 pi, right? Then maybe, right? That's pretty beautiful. That is really neat. So these are the epicycloids, and you can change b as well. B just grows this out, as you can see. Now, I'd like to also showcase how you get a path of travel. Although on something this size, the path of travel is going to be very, very hard to see. And also, honestly, it might be very challenging for you to even see it within this. So let's go ahead and take a timeout. And what I've done during the timeout is I just typed in the function for x and the function for y. I'm going to delete this epicycloid out. Okay. And then down below here, I'm just going to plot the functions f of t versus g of t. And that should give me the same epicycloid if I go from time, let's just go from 0 to 100 pi. There you go. So that's the same epicycloid. It's just, I wanted to have the functions named because I want to show you something. So now how do you actually see the path of travel? The way you can see the path of travel is by naming a different parameter, not a or b, but let's try the parameter c. And I'm going to plot the point f at c, comma, g at c. And I'm going to add a slider for c. And that slider, I'm going to start at 0, and I'm going to go to 100 pi. And I'm going to do very small step sizes, 0.00001 or something like that. I don't know if it'll allow for that, but whatever. Then I will click on animation properties, and I'm going to slow it way down. Now watch when I hit play, because the point you can see is right there. That's the initial point. Now hopefully it doesn't go too quickly. You can see it kind of zooming around, right? But this is how the curve got carved out. Very, very neat. So that's how you could showcase how, although you would never be required to do that on an exam, obviously, but it is kind of neat to see how a curve like this gets carved out. All you really need to do is define what x is as a function, f of t, what y is as a function, g of t, plot the point f of t, comma, g of t. It'll ask you at some point to label your parameters a and b, so that's what I did here. You can decrease those if you want. Ooh, that's pretty. And then I plot the point f of c, comma, g of c, and I allow c to move around. You can see in this case, here's what that does. Man, it's so beautiful. Isn't it really neat? I just think that's a gorgeous curve. Anyhow, so that's using technology to graph using Desmos. Now, the very last one I want to do here is one of my favorite parametric curves. So I'm going to do the same thing I did last time, which is I'm going to label the function for x. And the function for x is going to just be sine of the square root of 3. Hop outside that square root and call that t. So that'd be x. X is sine of root 3 times t. One thing you also want to do is turn off the graph on that so that you can't see it. G of t, which is the y value, will be cosine of the square root of 2, again, times t. And again, I'm going to turn off that graph. Notice I don't have A's or B's here. I don't really care about that. Now what I'm going to do is graph f of t, comma, g of t, the parametric curve. Notice I'm only going from 0 to 1. So let's go ahead and increase that and go from 0 to, actually, let's do a parameter here. Let's go from 0 to a. Now if you, let's set a to go from 1 to 200 step sizes of 1. Okay. So here's a equals 1. Now let's go ahead and see what happens as we increase what a is. I should zoom in because you won't be able to see the glory of it otherwise. As I increase a, you can see it starts to create what is called a tartan pattern. This is like a Scottish tartan pattern. Very, very beautiful. And let me just decrease a little bit. Let me get down to a equals 100 here. Okay. If you want to see the path that got carved out, you graph f of c, comma, g of c, add a slider for c, start c at 1 and end c at 100, and go by step sizes of, let's just say, 1/100th. Slow it down because otherwise it'll go too quickly. Press play. That's still way too quick, right? Let me see if I can slow it down even further. I can. So you can see that purple dot moving around. That's how it carves out this tartan pattern. Very beautiful. And if I pause it, run back and go to 200 and press play again, you'll still see how it carves out the first 100 of the tartan pattern. Very, very beautiful. So you can see that with parametric curves, you get some beautiful, beautiful patterns, wonderful equations. Not all of them have patterns, but this one definitely does. And so that's using technology, specifically Desmos, to graph a parametric curve.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.